electrification, the world now consumes over 20 million tons of copper every single year. And where does all that copper come from? Not from recycling alone, though recycling is hugely important, but mostly from mining deep deposits hidden inside the earth. These deposits aren't pure copper metal. Instead, they're ores, rocks that contain copper minerals like chalcopyrite, bornite, and malachite. Typically, copper ores only contain a small percentage of actual copper, often less than 1%. That means for every ton of copper extracted, miners must move and process hundreds of tons of rock. This is where the journey begins. Locating those deposits, digging massive mines, and then transforming ordinary rock into one of the most valuable metals on Earth. So, how do we actually find copper in the first place? The Earth's crust contains copper scattered almost everywhere, but only certain locations have concentrations high enough to be mined profitably. That's where exploration geology comes in. Geologists begin by surveying landscapes using satellite imagery, mapping rock formations, and analyzing soil chemistry. They look for signs of copper minerals on the surface, greenish stains of malachite, or bluish hints of azurite. But since the richest deposits often lie deep underground, scientists rely on advanced tools like magnetic surveys, seismic studies, and drilling core samples. When drilling, a cylindrical piece of rock is pulled out of the ground, often hundreds of meters deep. Geologists examine these cores to estimate the size, depth, and grade of a copper deposit. If the results are promising, companies spend years and millions of dollars conducting feasibility studies. They ask questions like, how much copper is really here? How much rock must be moved? What's the environmental impact? Can this mine be profitable for decades? Once approved, it's time to dig. And depending on the deposit, miners use two main methods: open pit mining and underground mining. The journey starts at the primary crusher. Here, gigantic rocks, sometimes the size of a refrigerator, are dumped into a machine with steel jaws. These jaws slam together with immense force, reducing boulders into fist-sized chunks. The process doesn't stop there. Secondary and tertiary crushers further reduce the pieces down to gravel-like sizes. Why so small? Because the smaller the particles, the easier it is to free copper minerals from the surrounding rock. After crushing, the ore heads to the grinding mills. Imagine enormous drums, each bigger than a bus, rotating day and night. Inside, steel balls or rods tumble with the crushed ore. As the drum spins, the heavy balls crush the ore into a fine powder. At this stage, it looks less like rock and more like wet sand or even muddy slurry. This fine grinding is crucial because copper minerals are often locked within the tiniest grains of rock. Now comes the ingenious part: separating valuable copper minerals from waste rock. Since copper minerals often have unique surface properties, miners use a method called froth flotation. This step is magical when you think about it. Out of tons of dull gray rock, we've now isolated a small but powerful concentrate brimming with copper minerals. But we're not done yet. The concentrate still contains sulfur and other impurities, so it needs to be transformed into pure, usable metal. At this stage, enormous conveyor belts and pipelines move the copper concentrate to smelters or processing plants. From muddy slurry, the journey is about to leap into the world of fire, heat, and chemistry. After concentration, the copper-rich slurry, now upgraded to about 30% copper, travels to one of the most dramatic stages in metallurgy: smelting and refining. This is where chemistry, heat, and human ingenuity combine to transform dull concentrate into glowing, usable copper metal. The concentrate, still containing sulfur and iron, is dried and fed into huge furnaces. Imagine steel chambers large enough to hold a small house, burning at over 200 degrees Celsius, 200 degrees Fahrenheit. The molten matte is then transferred to another furnace called a converter. Here, air or pure oxygen is blasted through the molten material. The oxygen reacts with the remaining sulfur and iron, driving them out as gas or slag. The result, a product called blister copper, so named because its surface appears blistered with bubbles of escaping gas. This blister copper is about 98 to 99% pure. But 98% isn't good enough for modern technology. Smartphones, electrical wiring, and medical devices demand ultra-pure copper, 99.99% purity. To reach this perfection, blister copper undergoes electrolytic refining. When the process is complete, what emerges are sheets of copper so pure they gleam like mirrors, ready to be rolled, drawn, and manufactured into countless applications. From ore dug deep in the earth, we've now produced one of the world's most essential materials. The copper you see in wires, plumbing, cars, electronics, even renewable energy systems like wind turbines and solar panels, all trace their origins back to this fiery transformation in smelters and refineries. If you've enjoyed this journey into the hidden world beneath our feet, imagine how many more stories the Earth is waiting to tell us. Subscribe to the channel, hit that notification bell, and join me as we uncover more secrets of science, nature, and the incredible materials that shape our modern life. Don't just watch, be part of the adventure. Every second, somewhere in the world, a light turns on, a signal is sent, a machine begins to hum, and behind it all is one unassuming component, the cable. From towering skyscrapers to underground data vaults, from electric vehicles to the smartphone in your hand, cables are the silent veins of modern civilization. But have you ever stopped to wonder, how do we make the things that make everything else work? How does raw metal become a lifeline of power and communication? In this documentary, we'll take you deep inside one of the most advanced cable manufacturing plants on Earth. A place where molten copper becomes signal, where plastic polymers wrap precision, and where every strand is tested, measured, and trusted. It's a world of heat, pressure, and accuracy, where a fraction of a millimeter can mean success or failure. If you're fascinated by the industrial backbone of modern life, don't forget to subscribe to Top Discovery 4K. We dive into the science, scale, and secrets behind the objects you use every day without even knowing it. Now, let's follow the journey of the cable, from copper to connectivity. Before a cable transmits power or data, before it's wrapped in layers of armor or plastic, it begins life as something raw, heavy, and silent: metal. At the heart of almost every modern cable lies one of two core elements: copper, the gold standard of conductivity; aluminum, lightweight, economical, and strong. Both metals are delivered to the factory in massive coils or rods, thick as a thumb and heavy as memory. These coils can weigh up to 5,000 kilograms each, and are often delivered straight from foundries or recycled from scrap processing plants. But this isn't just about melting and molding. Making a cable starts with purity. Even a trace of oxygen or iron in the copper can reduce its performance dramatically, resulting in heat loss, weak signals, or worse, electrical failure. That's why premium cable manufacturers start with oxygen-free copper or electrolytic tough pitch copper, refined to over 99.99% purity. The goal? Maximum conductivity, minimum resistance. And if aluminum is chosen, it's not the foil in your kitchen. This is industrial-grade aluminum, often alloyed with small amounts of magnesium or silicon for strength, then treated to resist oxidation. But conductors are only half the story. Wrapped around them will be layers of insulation, shielding, and jacketing, each made from custom polymers: PVC, polyvinyl chloride, flexible, fire-resistant, and inexpensive; XLPE, cross-linked polyethylene, tougher, more heat-resistant; TPE, nylon polyurethane, used in specialty or extreme environment cables. These plastics arrive in the form of pellets, small as lentils, stored in silos and fed into the process by vacuum systems and gravity hoppers. Colorants are added too, often vivid reds, blues, and yellows, to help identify individual wires inside a multi-core cable. Even color has a code here. Even color has a job. And finally, for heavy-duty cables, there's steel, either galvanized or stainless, used for armoring. Because in some places, a cable has to fight off water, pressure, fire, rodents, even time. All these materials, metal, plastic, steel, will soon come together to form something far greater than the sum of its parts. But first, the copper must be transformed. Coming up next, how a thick, stubborn rod of copper becomes a hair-thin wire that can carry electricity across continents. The copper arrives thick, solid, and unforgiving, coiled like a metal python, waiting to be tamed. But no cable can use copper in this raw state. It's too thick to bend, too coarse to carry precise signals. To become useful, it must first become thin, very thin. This is where the magic of wire drawing begins. The process looks deceptively simple. A copper rod is pulled through a series of holes, each one smaller than the last. But these aren't ordinary holes. They're precision-engineered tungsten carbide dies, hardened, polished, and set in perfect alignment. Each pass through a die stretches the copper, reducing its diameter and extending its length. From 8 millimeters to 4, then 2, then 0.5. Eventually, the copper is drawn down to just a fraction of a millimeter thick, thinner than a sewing needle, yet perfectly uniform. But copper is stubborn. As it's drawn, it hardens. Too much tension and the wire snaps. Too much heat, and it warps. So factories use emulsified lubricants, a milky solution that cools the wire and protects the dies. Without this, the dies would wear out in hours instead of weeks. And still, the process isn't done. Once the copper has been drawn to its final diameter, it passes through a continuous annealing furnace, a glowing tunnel of controlled heat. At around 400 to 500 degrees Celsius, the copper is softened at the atomic level. Its internal grain structure relaxes. The wire becomes more ductile, easier to bend, twist, and coil without breaking. This transformation, from stiff rod to soft, flexible wire, happens at speeds of up to 40 meters per second. Out the other end, the wire is cooled, dried, and wound onto take-up spools. Neat, gleaming coils that look almost like polished hair. Each spool is tagged, logged, and ready. What was once a chunk of metal is now a high-performance conductor, ready to carry power, data, or both. But most cables don't use just one strand. They use many. A single wire is useful, but in the world of electricity and communication, strength comes in numbers. That's why most cables don't use just one strand. They use several, twisted together in precise geometries that balance strength, flexibility, and signal integrity. This is where the process known as stranding begins. Inside a massive, rotating machine, resembling a mechanical spider, the individual wires from the previous step are drawn into formation. One by one, they're spun together, spiraling into a conductor bundle. But this isn't random twisting. The number of strands, the pitch of the spiral, and even the direction of rotation are carefully calculated, down to the millimeter. Why? Because how wires are twisted determines how electricity moves. It affects everything from electromagnetic resistance to heat dissipation. In power cables, stranding adds flexibility and ensures the cable doesn't break when bent or coiled. In communication cables, such as Ethernet or telephone lines, pairs of wires are twisted in exact ratios to reduce crosstalk, that annoying interference that garbles sound or data. Some cables use just 7 strands. Others, like high-capacity power lines, may use 37, 61, or more, layered concentrically for maximum flow. And then there's pairing. For multi-core cables, each twisted pair is given a unique color combination: red and black, green and yellow, blue and white. These colors follow strict international codes, allowing electricians and technicians to identify, repair, or install without guesswork. Once twisted, the strands pass through binders, thin tapes of polyester or nylon that hold the bundle tightly together. From this point forward, the conductor acts as one unit. Bending it no longer stresses a single strand. Twisting it no longer weakens the core. It becomes a unified body, the beating heart of the cable. But this heart is still vulnerable. Bare copper cannot survive the real world. It needs skin. It needs armor. Electricity is powerful, but without control, it's also dangerous. That's why every conductor, no matter how small, needs insulation. This isn't just wrapping wire in plastic. It's engineering a barrier between raw energy and everything else around it. Moisture, metal, people, the air itself. At this stage, the freshly stranded conductor enters one of the most sophisticated machines in the entire factory, the extrusion line. Here's how it works. First, plastic pellets, stored in tall silos, are vacuum-fed into a hopper. These tiny beads, made of PVC, XLP, or Teflon, are then melted at over 200 degrees Celsius, forming a thick, molten polymer soup. The molten plastic is pushed through an extrusion die, a tool shaped exactly like the cross-section of the final cable. The die surrounds the conductor with a perfectly centered layer of insulation, applied in a single, continuous flow. There's no stitching, no glue, just heat, pressure, and absolute precision. But the moment the plastic hits air, it starts to cool. To prevent cracking, bubbles, or uneven shrinkage, the insulated wire is immediately submerged into a water trough, chilled and calibrated to control the cooling curve. What emerges is more than just wire with a coat. It's a functionally advanced material, tailored to resist heat, water, voltage surges, UV radiation, chemicals, and oils. Different applications demand different insulations. In homes, flexible PVC, safe and affordable. In high-voltage lines, cross-linked polyethylene, XLPE, heat-tolerant and tough. In hospitals or aircraft, low-smoke, halogen-free compounds to protect lives in case of fire. To the naked eye, it might just look like plastic, but under a microscope, it's a shield, a seal, a silent protector of energy in motion. And every detail matters. Laser gauges along the line measure the insulation thickness 1,000 times per second. If it's even a hair too thin, the cable is stopped, flagged, and reprocessed. Because when you're carrying thousands of volts through a concrete wall or data through a server farm, there's no room for error. Armoring turns a cable into a mechanical survivor, capable of withstanding crushing force, chemical exposure, and even gnawing rodents. To do this, the cable passes through another machine that wraps it in layers of galvanized steel wires, corrugated metal tape, or even stainless steel strips. These metal jackets are applied helically or longitudinally, depending on whether flexibility or maximum protection is required. For marine applications, the cable may also be layered with bitumen, jute, or waterproof polymers, designed to survive decades under the seabed, wrapped in mud, salt, and silence. In some cases, armored cables are also fire-rated, built to withstand 950 degrees Celsius for 2 hours without losing power transmission. These are the kinds of cables you see in nuclear plants, subway tunnels, and military command centers. By now, the cable is internally complete. It has a core conductor, insulation, shielding, and armor, but it still needs one last thing: a skin, something to hold everything together, something the world will actually see. The outermost layer of a cable is more than just a wrapper. It's the first line of defense against weather, wear, chemicals, and time. This layer is known as the jacket, and it's applied through the same high-speed technology that once insulated the core: extrusion. Pellets of PVC, PO, polyurethane, or low-smoke zero-halogen compounds are fed into a hopper, melted, and forced through a die. But this time, the die is wider, designed to slide the molten polymer over the entire structure of the cable, like a glove. As it coats the cable, the polymer fuses tightly, locking all the inner layers into one solid, sealed unit. The newly jacketed cable then passes through a cooling trough, where precise water jets harden the jacket without warping it. Sensors track every detail: diameter, centering, thickness, even surface texture. Depending on the application, the jacket may be glossy for low-friction installations, textured for grip and abrasion resistance, color-coded for voltage, function, or brand. In many cases, an inkjet printer adds vital markings along the length: voltage rating, conductor size, flame class, standards met, production date, and meter markings critical for installers in the field. At this point, the cable is sealed, protected, and ready to face the world. But it's not quite finished yet. As the cable exits the jacket extrusion line, it moves at speeds up to 80 meters per minute, a blur of engineered material. But precision doesn't stop just because production is almost over. The cable now enters a final cooling stage, using calibrated water baths and forced air dryers to stabilize shape and material hardness. This ensures it won't deform during spooling, shipping, or installation. Then comes the printing station, where non-contact inkjet systems mark every meter with real-time data. Production lot, plant location, quality inspector ID, compliance logos, UL, CE, ISO. These markings turn each meter of cable into a traceable component, auditable down to the minute it was made. Next, the cable is cut, either into standardized industrial lengths, like 100 meters or 305 meters, or wound onto massive steel or wooden reels for long-haul applications. Each reel can weigh up to 5 tons, especially for medium voltage or armored cables. Finally, every reel is wrapped, strapped, and tagged, ready for its most important test of all. Before a single cable leaves the facility, it must prove itself. Every batch goes through rigorous testing in specialized labs, each test designed to simulate a worst-case scenario. High-voltage dielectric test. subjecting cables to 1000 plus volts to verify insulation integrity. Conductor resistance test, ensuring the wire carries current within strict ohmic limits. Flame retardancy test, burning sections of cable in vertical chambers to ensure self-extinguishing properties. Cold bend and impact tests, flexing the cable after freezing to -40°C. Signal integrity test, for data cables measuring attenuation, crosstalk, and impedance. Chemical resistance test, soaking jacket samples in oil, acid, or salt spray. For safety-critical cables, X-ray inspection or microtome slicing is used to examine the internal structure without damaging the sample. Every result is logged into a digital quality database. If even a single test fails, that batch is quarantined for investigation, rework, or recycling. Only cables that meet 100% of specifications are approved for shipping. Each one is labeled with a QR code or barcode linked to a digital certificate of compliance. Because in the world of energy and infrastructure, there are no second chances. Copper, the reddish-golden metal that powers our homes, our phones, our computers, and even our cars. Every year, the world consumes over 25 million metric tons of copper. But did you know that nearly 1/3 of it doesn't come from mines? Instead, it comes from recycling. In today's episode, we'll step inside a supergiant copper recycling facility where millions of old wires are stripped, shredded, melted, and reborn as brand new copper. Ready to fuel the modern world again. This is recycling on an unimaginable scale. Before we dive into today's mind-blowing journey inside a supergiant copper recycling plant, make sure you hit that subscribe button and turn on the notification bell. On this channel, we explore the hidden world of mega factories, incredible processes, and the amazing ways everyday things are made. Trust me, you don't want to miss what's coming next. Copper is one of the most valuable metals on Earth, not just for its conductivity, but also because it can be recycled infinitely without losing quality. That's right, copper can be melted down and reused again and again, always as good as new. Mining fresh copper ore is expensive, destructive to the environment, and energy intensive. But recycling copper? It saves up to 85% of the energy compared to mining. That's why copper wires, pipes, motors, and even tiny scraps are collected worldwide to be reborn. And where does a lot of this copper come from? Discarded electrical wires. Inside this plant, mountains of tangled multicolored wires, once used in homes, electronics, and vehicles, wait for their second life. It all begins with trucks rolling in. Carrying tons of used copper wires, these might come from construction demolitions, old appliances, or even massive utility upgrades. At the facility, workers and machines sort the incoming wires. Thick, high-purity copper cables are separated from mixed wires that contain more insulation and impurities. Everything is weighed and tracked. Even at this early stage, nothing goes to waste. Every kilogram of copper has value. Next, the wires move into industrial wire stripping machines. Imagine giant rollers with sharp blades peeling off the rubber or plastic insulation at high speed. Some wires are stripped clean, others are shredded into tiny fragments. The shredded mix is then fed into a granulator, a powerful machine that tears the wires into small pieces, separating copper from insulation. On one side, you get shiny copper granules. On the other, heaps of plastic waste. But here's the mind-blowing part. With advanced separation systems using airflow and vibration tables, this plant achieves up to 99.9% purity copper recovery from shredded wires. The clean copper granules are then transported to the melting furnace. Here, temperatures soar above 1085 degrees Celsius, 1980 degrees, the melting point of copper. Giant crucibles swallow thousands of kilograms of copper, glowing molten red as impurities float to the surface. Skilled workers remove the slag, leaving pure liquid copper. This stage is mesmerizing, a river of glowing metal, ready to be reborn. The molten copper is then cast into giant shapes, depending on its next use. Sometimes it's formed into copper rods, which later become new wires. Other times, it's cast into cathodes or billets, used for industrial products like motors, electronics, and even coins. Each cast piece is cooled, cut, and inspected for quality. The copper that was once a tangle of waste wires is now indistinguishable from brand new copper mined from the earth. But what about all that insulation stripped from the wires? Surprisingly, it's not wasted. The plastic is shredded further and sometimes used as fuel in cement kilns, or recycled into other products like mats or piping. In this circular process, almost nothing is thrown away. This one facility alone can recycle hundreds of thousands of tons of copper wire every year. Globally, copper recycling saves over 100 million megawatt hours of energy annually, enough to power entire nations. Without recycling, copper would quickly become scarce, and the cost of electronics, cars, and renewable energy infrastructure would skyrocket. As the world electrifies, building more solar panels, electric vehicles, and wind turbines, the demand for copper is expected to double by 2050. Mining alone won't be enough. The real secret weapon is recycling on a massive scale. From an old phone charger to a skyscraper's electrical wiring, every piece of discarded copper has a future. And giant recycling plants like this one ensure the cycle never stops. If you enjoyed discovering how millions of wires are reborn, don't forget to like this video, subscribe to our channel, and hit the bell icon so you won't miss the next incredible journey into the world of mega factories and mind-blowing processes.